So what I wanted to do was showcase parallax mapping and the different forms of that, and that's all based on top of normal mapping. Parallax mapping was accredited to, man, I'm going to murder this name, but Tomomichi Kaneko and his research team out of the University of Tokyo in 2003, I believe. So what I got here basically is my maze project with different mapping techniques applied to it. So this is just the normal mapping going on now. I know the textures are kind of god-awful. There's only, certain things going on there. So basically, I'm going to switch here. That's just the normal. Here's parallax. So you can see from the normal, we get some type of depth on the mapping. When you use parallax, it actually cuts in a little deeper. Don't worry about this blobby stuff here. That's just, since parallax is based on my depth mapping, it's really cutting in there and it's making it really awful looking. But that can all be adjusted by smoothing out the depth mapping that you have there. So that's parallax. I'm going to bump it to steep parallax, which is actually, it looks like it went back to normal, and that's only because steep parallax uses different parallax layers. So it's viewing it at the direction of the eye onto the diffuse map, and then when you hit the parallax, it actually cuts and takes a layer, which is the delta layer between the diffuse map and then your normal map where it's showing the depth technique. So I'm going to go ahead and bump up the layers here. And as you can see, it really cut in. And you can actually see these little rivets right here. Those are actually the different layers that the steep parallax is using to show the depth there. And the more layers you go, the smoother it's going to get. But like I said, my textures are pretty crappy and the depth map is really bad, so this giant black blob here actually cuts in when it shouldn't. But that's all just needs to be adjusted in the depth mapping. So I'm going to go back a couple layers here so we can kind of see these little lines, those different layers there. Maybe bump it back a couple more. Now we can really see it. And that's with the steep parallax. Now we're going to go ahead and apply parallax occlusion mapping. And you see how that smoothed that out? That's because parallax occlusion mapping takes one of those layers and then takes the delta between the next layer and the delta between the layer below it, and then adds another layer in there and really smooths it out. It's kind of hard to see how this actually applies really well on the maze here. I mean, you could see it kind of, but it's just like this right here. That's because I didn't actually break the wall. It gets applied all one texture. These should actually have their own texture built for them, but baby steps. I'm a pleb when it comes to this stuff, so, pretty new. Just gotta keep going at it. Spend some time on the mapping. I just really wanted to show this mapping technique. I think it's really cool the way it cuts that depth in there. Also with this, I used a form of indexing so like all the data points, for each point there's a set of data on there, and then when it draws the triangles for the shared points, it indexes back to that single point, so there's less overhead on the shaders. I also use, let's see if it's in here. Yeah, I actually use the Atlas technique for the fragment shader here. And that's so that the fragment shader only has to load the one texture, or the one source file, or bitmap, or whatever you want to call it. And then that actually holds all three textures, all three normals, all three depths in that one file. It's just a way to save overhead. Very efficient. I'm going to go ahead and flip over to this cube here, which is kind of what I built as a fallback in case the maze wouldn't work. And also it's what I started with, just to make sure that I could get it to work using the tutorials. So this cube right here, I think, is just, yeah, it's just using the normal mapping here. I'm going to go ahead and spin it. So you see right here the normal mapping. Once you start spinning and the light's not really hitting it in that certain direction, it looks really flat. This is where parallax really comes in. I know it looks kind of crappy right there. So like when you spin right there, it still kind of gives it depth. And then this right here, this crappy look, how it kind of looks like there's an opaque layer. And you can see this one layer right here. It looks like there's actually two layers on there. Well, this one opaque-ish layer right here, that's what the parallax is taking. So that's what it thinks, kind of like what it is trying to portray down on top of that layer based on the calculations. So that's why they started doing even more with that and doing steep parallax. And there, you can really see the layers that we saw in the maze showing up on there. But you can also see how it actually defines more of the depth, so you don't really get that opaqueness going on, that translucent layer. And you could, I don't know how many actual layers the my GPU will handle, at least the WebGL. I do a max of 32. I think that looked pretty good. That's also what the tutorial that I was basing most of this off of used. So that's with just steep parallax, and as you can see, it's still pretty good. You're obviously still going to have issues, but that's probably just because of limitations of WebGL. And I'm not, we're not in actual OpenGL on C++. And, I'm going to take it back down to where it had, you can see all those crappy layers there. About right there. And we'll go ahead and put the occlusion mapping on there. And you see how that really smoothed it out, just using the same layers as the steep parallax mapping. The more layers you add, the smoother it gets. There's also this weird little issue here where it's looks like it's bumping in and stuff. There's all those little textiles there that are crappy, and that's actually in the bump map. I went in and checked, and there's pixels that aren't specifically white or black. They're kind of a weird shade, so that could be fixed, but I didn't feel like going through one pixel by pixel and adjusting everything. And this normal mapping and bump mapping was basically taken from the tutorial. I just wanted to show that because you can actually see the definition a little better than you can with my handmade maps. Shows up a little better. We can look at the code here. So basically, the principle of parallax mapping is to use tangent space. So that way, pretty much everything for mapping is done inside the shader, and it's a lot more efficient than doing all the calculations outside in like JavaScript or your source language. So basically, you give it the geometry, you give it the texture coordinates, the UVs. You give it the tangent and bit tangent coordinate of the geometry position, and I actually compute that in this little subcode thing I made. So that one actually took a while because the thing I was basing it off of, they like hard-coded their tangents and bit tangents. So my calculations weren't matching what they had hard-coded. And it took quite a while of writing down tangents, bit tangents, doing all the calculations by hand over and over just to have it not working right. So then I took the tangents and bit tangents that I calculated based off of this and plugged it into the tutorial, and it worked just fine. So there was 4 days wasted on my end, but hey, that's learning, right? So yeah, basically you compute those, then you send that back in to the shader here, the fragment shader, and that will actually compute the normals down here. It'll take the normal, which is just the cross product of the tangent and bit tangent. It's more efficient to compute it in the shader than it would be in JavaScript, so that's where we're going to handle that. And then we take the tangent space fragment position, which is pretty much just the model matrix times the position matrix. And then we do a tangent, bit tangent, and normal matrix inside here by taking the normal matrix. That is actually, we have another normal matrix that's based off of what the movement is, and that's all this is right here. That's just the new normal of the movement. And then this is the normal of each point in the position buffer. So we get that vector, normalize it, do the same for the bit tangent, the normal, which is just the computed normal on the new normal, make that, and then we make this tangent, bit tangent, normal vector, and this is pretty much what you need to do mapping. The parallax mapping is this right here. So you get your lighting position. Mine's just arbitrary, but it's just one light, just the ambient light pretty much. But if you had other lights in there, you'd have to take all those vectors and compute them into this light position vector, so it knows which way to shade out this geometry and stuff in there. So you take that. You could also take your view position. Like if I was using like a third-person controller where the mouse was moving the camera around, I'd have to take that into account right here. But I'm not. I'm making the geometry move for the camera, and we're going to use that as the camera. And then this fragment position is what we computed up here, is the tangent space fragment position, and you just multiply that by the TBN vector, which is the tangent, bitangent, and normal vector that was all computed up here, and you take its transpose. And then, so that just gets passed down here into the fragment shader. This is where the fun stuff happens. So we got our textures there, we get our bit map or our diffuse map, the normal map, the depth map, and then the stuff that was computed up in the vertex shader gets passed down. The texture coordinates or the UVs, those get passed down. And then you have your number of layers, your depth scale. Those are what is going on when we have that layering issue right there. So right now, the number of layers would probably be at like 4, and that's what we're getting shown up with that. Excuse me, I'm getting over a cold, so I probably sound awful. So this parallax function here, what we do is type 1 is just normal mapping. So like we send in the UV, which is essentially just the texture coordinates. So that pretty much just sends back the texture coordinates. So that's just going to be our normal map pretty much, which normalizes down. And then we can, if we're just using parallax, we compute this depth here, and then that's our depth map, and that's where it takes that one layer right there. Let me spin it here. That translucent layer that we have there, that's what computes that, and that's actually halfway between the actual face here and then the depth face that we have there. It's taking that and putting that right there. Then we got the advanced parallax mapping, which is what we're looking at on the steep, where we take the different layers. So it basically does the same thing as a parallax mapping, only it does it like however many times you tell it to do the layers. So like we have 4, so it does that in 4, and then spaces them out evenly from there. Excuse me. And then the parallax occlusion mapping, that's where we are pretty much taking those 4 layers and then adding 2 layers on top of each, which are the deltas. It's the delta layer between, like this layer and this layer would have the delta layer, so one right there and one right there. And that really smooths it out a lot better. And then of course you gotta, take your light direction, your view direction, which, this one was pretty arbitrary. Just one light. Geometry moves around cameras, so there's nothing too special using that. But using that later on, moving into more advanced camera and lighting stuff, that's probably going to be a pain in the butt to deal with, which will probably take me a lot of time to figure it out. That seems to be the normal for me when it comes to this stuff. Like I said, I'm a pleb. I got no problem with that. I'm having fun. I'm learning. And basically, to me, that's what this is all about. So once you get your parallax, I just store that in Vec2 UV. You got to go ahead and apply that to your texture. So you get that parallax mapping, that applies to your diffuse texture. So that's what gives you that depth looking stuff there. And then you multiply it by the ambient. Come down and multiply it out by the ambient light. And then this is the big thing right here. So you take that texture, that UV you computed with your parallax, that text one, that's your normal map. Or, well, that's my normal map, you want to call it texture. Oh, I'm missing it. Oh, here it is. Right, and so it's the UV RGB values. I should have mentioned that. So the red, green, blue. I'm sure you guys know what normal maps do. So then you got to multiply that by 2.0. And then you take all of that, and you have to subtract this 1.0. We can actually subtract more off of here. It just really messes with the map. This is like the standard way to do it. I mean, we could play around with it. I know I was. Let's go ahead and refresh it. You see? It's basically through the, the depth and everything's there. It's basically through the lighting. Is what it looks like. Or another way I think of it is that it's like passing the back facing on. So 1.0 is usually pretty good. Then yeah, that's my experience in parallax mapping. Hope I didn't bore you guys too much. If you have any interest in it, it's fun to play around with. It's very useful to get, geometry cut in where you can't actually afford to have any more triangles in there. So it's a very efficient and useful way to add depth and texture to your models without actually adding in more, I can't think of the name, I'm just calling them triangles, but that's not actually what they're called in 3D modeling. I'm all hopped up on cold medicine, so sorry about that. But yeah, go out and look up some tutorials on parallax mapping, play around, have fun. If you do use it, I strongly suggest that you do the indexing. Actually, I could show you that real quick while I'm thinking about it, because that one took me a while to get sorted out too. So basically, it's an index buffer, and then you pass in your total number of vertices, but the point data is only so many. So, like right here, you have these point data. Where do I build it somewhere? I call it vert triangles, and that has all my points for the triangles. Like each face of the cube has 4 points, but there's 2 triangles on there. So in the points buffer, there's only the 4 points, but this vert triangle actually has 6 things per face, and that's when it indexes. That's what the indexer does. So it says, hey, point 0, go grab point 0. Point 1, go grab data for that. Point 2, go grab that. Oh, I'm back at point 0, grab that for this triangle. Without actually having to store, 6 points of data inside like a points buffer or whatever. So yeah, learned a lot, had fun, good class, lots of headaches, lots of heartbreaks, but that's learning. I like this stuff. Hope you guys too. Alright, bye.